Hello everyone, I'm Zhao from Colorado School of Math. With Rina Zhu, we are going to present our work, Crossing Reality, Comparing Physical and Virtual Robot Deixis. Because robots have physical embodiment, the human-robot interaction community has focused on nonverbal cues. For example, here we have a non-robot using eye gaze to direct your attention to the blue block. It also used our movement to move its arm towards the object to make the transition smooth. Specifically, it leverages deictic gestures, pointing at the object to refer to it. Studies have shown that they work very well, improving task efficiency and subjective experience. However, not all robots have arms to express those proven nonverbal cues. We have mobile robots like the delivery robots on the left moving on the streets, and drones to help in search and rescue tasks. These robots also need to communicate objects to humans. The delivery robots need to provide directional cues, and the drones on the right need to tell us where the object is after it is found. One simple solution is to mount arm onto those robots. However, it may bring more problems. We do mount robot arms to some mobile robots, but if they don't, those arms will cost over $10,000, and usually more than that. It also doesn't make sense to mount an arm solely for communication purposes, which is particularly true for drones. After we mount those arms, it brings safety issues, as they will move around humans and the arms may hurt humans. In our work, we propose adding an augmented reality virtual arm. As you can see, we mount the virtual arm on top of this mobile robots here. So people wearing an AR headset can see the mobile robot point at objects to communicate. Now, you might be wondering, is that really a good idea? Is the virtual arm better than a physical arm? Before this work, the answer is that we don't really know. AR researchers found that whole agents in AR didn't really have a negative impact. But HRI researchers found physical robots perform better than those on-screen agents, both objectively and subjectively. So for AR appendage, which is a mixture of virtual and physical, how can we make sure it is better? Another problem is that there is a reality mismatch issue. As you can see here, a virtual arm is pointing at a physical reference, while this virtual arm that is crossing the physical reality have a negative impact. To answer these two research questions, we looked into two factors, physical virtual arm on the left and the physical virtual reference on the top. So on the top, you see a physical arm pointing at either a physical reference or a virtual one. On the bottom, you see a virtual arm pointing at either a physical or a virtual reference. Here are more experiment details. It followed a phasing subject study with full counterbalancing. We recruited 36 participants and measured both objective and subjective measures, accuracy and efficiency, social presence, anthropomorphism, likability, warmth, and competence. We also used the Bayesian analysis framework because it can also provide evidence when our conditions perform the same.
I'll start with our result for the two objective measures, accuracy and efficiency. So accuracy here simply means how accurately the participant was able to identify the correct referent, and efficiency here is measured through reaction time, with a longer reaction time correlating to a lower efficiency. So we found that arm and referent virtuality really doesn't affect accuracy and efficiency. And similarly, when reality misalignment occurs, meaning, for example, a physical arm is trying to gesture towards a virtual referent, accuracy and efficiency also are not affected. And in the two figures here, we're showing the mean value for accuracy and reaction time across conditions. And just as a reminder, in different conditions, the first letter is referring to the virtuality or physicality of the robot arm, and the second letter is referring to the physicality or virtuality of the referent. And as you can see, there really isn't a significant difference across conditions. Now moving on to subjective measures, We measured 5 metrics in total. So for social presence, likability, competence, and warmth, we again found that arm and referent virtuality, really doesn't affect these 4 metrics. And similarly, when reality misalignment occurs, these metrics are also not really impacted. I do want to spend a little more time on anthropomorphism. We found strong evidence to show that anthropomorphism is significantly higher for a virtual arm compared to a physical arm. And a physical arm could be more anthropomorphized when it's gesturing to a physical referent compared to a virtual referent. And here in the figure, again, we're showing the mean values across conditions. And as you can see, the 2 conditions where virtual arm is used, anthropomorphism rating is higher compared to the conditions where a physical arm is used. So when trying to interpret this sort of difference, we thought this could possibly be caused by the mechanical movement and sound of a physical robot arm, or rather the more silent and smooth movement of the virtual arm that could possibly be offsetting this penalty to anthropomorphism that the physical arm could be suffering from. So what are some of our main takeaways? We found that AR virtual arm, when performing gestures, even cross-reality gestures, could offer equivalent task performance, is viewed as socially present, competent, warm, likable, but is distinctly more anthropomorphized compared to a physical arm. We also hope that this study could provide some assurance if you are considering using a virtual arm to enable gesturing in robots, even if it's cross-reality gestures. And that's the end of our talk. Thank you for tuning in.